So here we have a question which appears to be about probability. Rebecca invents a game with 2 dice, which have their faces colored the same way. 3 red, 2 white, 1 black face. She rolls both dice and wins if she throws 2 red faces, and loses if she rolls 1 or more black face on the uppermost face of the dice. If she gets neither, then she rolls again, and the game stops when she wins or loses. Okay, so before you look at the question, you need to clearly understand what's happening here. We've got 2 dice. Their faces are colored the same way. 3 red, 2 white, 1 black. So 6 faces, 3 red, 2 white, 1 black, total of 6. So quite clearly the probabilities are going to be listed out for you. The probability of red is going to be 3/6 or a half. The probability of white is going to be 2/6 or a third. And the probability of black is going to be 1/6 or a sixth, assuming that is a fair dice. Now she's got 2 dice and she rolls both. And she can either win if it's 2 red faces. She can lose if she rolls 1 or more black face. So black is bad. Any black, 1 or more black. And if neither, then she goes again. She just repeats. Show that the probability of winning in 1 throw is a quarter, and the probability of losing in 1 throw is 11/36. Okay, so to win, you need 2 reds, and you assume the 2 dice are independent. So the probability of red is the probability of red times the probability of red, which is a half times a half, which is a quarter. That's the probability of the win, right? So here is your probability of winning. Your probability of losing in 1 throw is 11/36. Well, it's an or, right? So your probability to lose, you basically need to get a black on either dice. So it doesn't have to be both. It could be either. So it's at least 1 black. So the probability of at least 1 black probably could be thought of as all possibilities, right? 1 minus no blacks. And so just in case there's any sort of confusion, you could also draw a tree diagram to show what this means, but let me know if that will help. But yeah, you can have 1 minus the probability of no blacks, which means you've got 1 minus the probability of not black times not black, which is 1 minus, well, not black is 5/6, right? If I don't care about if it's red or white, as long as it's not black, well, then it's, 5/6, right? That's minus 5/6 times 5/6, which means it's 1 minus 25/36, otherwise known as 11/36. So that shows us, therefore, that the probability of losing on the first throw is 11/36, as requested. Now they ask, what is the probability that she wins in the first or second or third throw? Okay, so a tree diagram may be helpful here. We'll keep in mind what we've said, right? So we've said that she's got 6 faces. We said that the probability of red is a half, the probability of white is a third, the probability of black is a sixth. We've worked out that for a round, the probability of win, otherwise known as red, was a quarter. The probability of lose, otherwise known as any black, at least 1 black, was 11/36. And so we might also think of what the probability of neither is. Given your only options are win, lose, or neither, it will probably be easiest to just subtract. So that's 36 minus 9 minus 11. So it's really 16 over 36, otherwise known as 8 over 18, or 4 over 9. All right, so a tree diagram may be helpful. We've got the start, and you've got round 1. So round 1, she could either win, she could lose, or she could have neither. Now, I might not bother drawing out all the branches of the tree diagram just to save myself a bit of space, but the win, we know for a round is a quarter, the lose is 11 over 36, and the neither is 4 over 9. And remember, if she's won, then she stops. So if she stops, there's nothing happens after she wins. And if she loses, nothing happens either. So we don't really need to draw any more branches here. So we just need to continue after neither. Well, for neither, she could again win or lose or neither. That is possible. But I don't care if she loses, in the sense that I'm not interested in that probability. I'm interested in her winning on the first, second, or third throw. So I'm not going to draw out the full tree diagram. This is round 1. This is round 2. I'm not including the fact that she could lose here because she could, but I don't need that probability, so I'll leave that. What I'll do now is I will now think of round 3. Again, she could either win or she could lose or neither. But that doesn't really worry me, right? I'm not really concerned about that. I'm really only concerned about her win here, her win here, and her win there. That's all I care about. So the probability that she wins in the first or second or third throw, okay. So the probability that she wins in round 1, or win in round 2, or win in round 3 is basically the probability of winning round 1 plus the probability of winning round 2 plus the probability of winning round 3. Well, the probability of winning in round 1 is quite clear because that's a quarter. We've already worked that out. But for her to win round 2, she would firstly have to, well, I guess, have neither in round 1. So it's the probability of a neither then a win. And then for her to have a round 3 win, it's the probability of a neither win. Now the probabilities are quite clear. The neither is 4/9. The win is a quarter. They're all sort of independent. So that means it's a quarter plus the probability of a neither times the probability of a win, plus the probability of a neither times the probability of a neither, plus the probability of a win. Hopefully it's all quite clear at this point. And that's when you can just use your calculator to work that out for you. Give you an answer of 133 over 324. So the probability is that. And that's how you do that question.